Okay, we're going to take a look at some more area between curve problems. So there's two questions I've got for you here, and this first one is a great recap of kind of our day one exploring this. And this is going to be a calculator-friendly question. So go ahead and grab your calculator, and you can totally try this problem completely on your own. I can't put my calculator on the screen, so I'm going to talk you through some things. Pretty typical with these that you are given a picture, if this is like a free response question, that they'll actually give you a graph. Now you're going to have to go ahead and graph it yourself, but it helps you out with kind of some things like window, and I should have marked a few things on here, so we'll label my axes. This is y equals 1. So just kind of identifying what we have here. We're trying to find the area between f of x and g of x and bounded by the y-axis on the left. Now, if you actually graph this, the f of x function oscillates and keeps going up and down. So there's actually many regions. So this is sort of helping you figure out what it is that we're trying to do in an easy way. Sometimes it's hard to put into words. So we've really got two regions that we're looking at here. And the first one is this region in here, and the second one is all of this. So we're definitely going to have to find our intersection points, so I would encourage you to go ahead and graph those two functions. I like to kind of make a note to myself that, okay, I've got y1 here and y2 here, just so that you know which one you've called what in your calculator. So go ahead and graph those. Make sure you've got your calculator in radian mode since we're dealing with a trig function. And then we're going to need to find the intersection points. So that's kind of the first thing that I'm going to do is, and it helps me, especially if this is a free response question, to kind of save yourself some time if you know you need to find those anyways, and then you can work on setup of the problem. So to find intersection, assuming you already have those in your calculator, obviously pause the video and do that. y1 and y2. Intersection points, to find the intersections. Second, calculate. I think you guys are good with that. So second, trace are the commands on your calculator that you're going to do. That gives you the calculate menu. And then you want the intersection button, intersection option, which is option 5. And then we need to get two intersection points. So a lot of times we like to label these in some way, and we're going to want to store these values in our calculator. So I'm going to label these. And this might be a weird choice, but I'm going to label them A, comma C, and B, comma D. And then I'm going to store, I actually only care about the X values, right? So I'm going to store the A, the two X values as A and B. And I'm just putting the C and the D there kind of so that I've got a coordinate point, because it feels awkward to just put A if I'm trying to represent an X value. So I want you to go ahead and get those two values. Once you get the first intersection point, then recall that if you go, so that's showing up on your screen, recall that if you go back to your home screen, second quit, and then you type in this in your calculator, X, the arrow, which is the store that's right above the on. So it actually looks like this on your calculator, is what it looks like, but it'll show up on your screen as just an arrow. So X store, and then type alpha and a letter. So I'm putting mine as A since that's what I said. And then you're going to do the same thing for your second intersection point. So go back to your graph screen, calculate your second intersection point, and then go ahead and do X store as B. And if you write those down, I don't have those at the moment. I did them and I put them in my calculator, but I would recommend that you actually put A equals and B equals, and then you write out all the decimals that your calculator shows, and that's showing what you're storing and that you're using the exact values. That is the expectation, and they want to know that you're not rounding to 3 decimal places. We round at the end of the problem, so we don't want to round. Those are going to become our limits of integration. We don't want to round those. Okay, so go ahead and do that, and then take a minute and set up what your integrals are going to be. So how are you going to get the area of those two regions? And then we'll check. Cool, so I'm going to go ahead and label. I kind of like to color code for myself. This is my f of x that's given to me, and then my g of x is that one. So like I said, we're going to need two integrals. So integral of the yellow region is my top curve is my red, which is my g. I absolutely recommend, instead of rewriting the whole function, that you just use those defined f's and g's. It's going to save you time. It's going to prevent you from making a typo by writing the wrong thing and then end up putting it in your calculator wrong. And then my second region is going to be the reverse. So that's going to be my f minus g. And then we just need to put our limits of integration. So the first one, we're going from x equals 0 to x equals a. And then the second one, we're going from x equals a to x equals b. If you want to use some parentheses around that, you can. And the beauty of this is you're going to go right to your home screen on your calculator. I absolutely recommend that you type this in as one great big entry. And the only difference is that where we have g of x, we're going to type in a y2. So on your calculator screen, it should look like this. And all we need is one answer. So answer should be, to 3 decimal places, 0.475. So that is the entire question. Make sure you've got everything typed in correct. And then when you're ready, we're going to move on to one more example. This one's going to be a no calculator question. So get ready to do some calculus. So find the area of the region enclosed. So this is one where we've got no graph, and we're going to have to graph it. And recall that if we're doing a region enclosed, then we are going to have to find some intersection points. So I usually like to start with a sketch. This helps me just kind of think through the problem. So x equals y squared, that's interesting because they're not giving it to us. Solve for x, but recall that if we take the square root of both sides, that's the same thing as y equals square root of x, but technically we're inserting a plus or minus. So that's going to be the same thing as y equals positive and negative square root of x. So that's going to be graphed as this and this, also known as your sideways parabola, is the other way to think of it. X equals y squared. And then y equals x minus 2. So we've got, and we've got a y-intercept of -2, and we've got a slope of 1. So what that puts us here, something like that. So I'm going to go ahead and find the intersection point there. So we can go with our positive square root of x and negative square root of x are both intersecting that, or we could, so let's go ahead and do, I guess we could do this either way, but like I said, when we're doing the first one of these, we don't need to find the x and the y value. So since I'm just worried about the x, it makes more sense to take my solve for y version, and I'm going to square both sides. I'm going to get x equals, remember, we're squaring that quantity, not distributing the squared. We get a quadratic equation, so don't forget what you learned in Algebra 1. Algebra 2, you are setting this equal to 0, which means I'm subtracting x. X squared minus 4x minus another x is minus 5x plus 4, and then factoring that. So I'm getting 2 intersection points, and I'm going to take a look at those and recall that we have, so really it's my positive and my negative square root. Since I squared it, I'm finding both of those. And what it looks like, we've got one here and one there. So there's my x equals 1. That looks pretty fabulous. So 1 comma something, it looks like a -1. I don't really need that number. And this one is my 4 comma something. so I am about ready to do my, I am ready to set up my integrals. And remember that we need to do top curve minus bottom curve. So I'm noticing right away that my top curve is the same, but my bottom curve changes. Because again, I actually have three functions here. So if I take my positive square root of x and make that my top curve, that's cool, but my bottom curve is actually the negative square root of x for this first portion right here. So that's until we get to that x equals 1. And then my bottom curve changes to my linear piece for the rest of the region. So looks like we're going to need two integrals again. So I'm going to go from 0 to 1, and that's going to be my blue curve, which is my y equals positive square root of x, minus my red curve, which is my negative square root of x. So obviously I'm going to go back and change that to plus or positive. And then my second, I'm just going to go ahead and get my setup, and then I'll just crunch the integrals out. I'm going to go from 1 to 4, and that would be my top curve is still that radical x, minus, and then my bottom curve is my x minus 2. Be careful here. We're subtracting that entire curve, which is really my line. So I'm going to need the parentheses there. Setup looks golden. So now we got to hold ourselves accountable to, can we do the math? So we've got radical x plus radical x. Whoops, that's 2 radical x. And I'm going to write out all my thinking here. I'm just going to kind of work down the first one, and then the second one, I'm going to add my two answers at the end. So I'm thinking 2x to the 1/2 power. And actually, we can pull that 2, we can pull that 2 out. So we don't have to worry about it in there. So let's make this simplest integral that we can. 2 integral from 0 to 1 of x to the 1/2. And now I'm about ready to do my integral. So x to the 3/2 over 3/2, which is times 2/3. And the original 2 out front. And I'm going to evaluate that from 0 to 1. So for the sake of tightening things up a tad, let's make that 4/3 x to the 3/2, evaluated from 0 to 1. So that's me now. Fundamental theorem of calculus. I grab my upper limit of integration, plug that in. So I've got 4/3 times 1 to the 3/2 minus 4/3 times 0 to the 3/2. And that's giving me 1 to any power is 1. So I end up with 4/3 minus 0 to any power is 0. That goes away. So 4/3 is it for the first part. Okay, now part 2. So I've got this set up for myself, and I just need to, like I said, make this integral friendly. So x to the 1/2 minus x minus a negative is plus 2. And now I'm just going to integrate all of those separately. So integral is going to be x to the 3/2 over 3/2, or times 2/3 minus x squared over 2 plus 2x. We don't need that plus c if you're like wanting to write a plus c, and the reason is that I'm going to, when I use that fundamental theorem of calculus, I would have had a plus c here and a plus c here, which ends up being a minus c because of that subtraction sign. So they cancel each other out, and that's why we say we don't need it. Okay, so I'm ready to plug in. So again, I like to set up for myself this kind of subtraction. The plus sign is just because I've got that other part there. I'll come back to that in a minute. So I've got 2/3 times x to the 3/2. This time I'm plugging in the 4, upper limit first, minus 4 squared over 2 plus 2 times 4. 2/3 times 1 to the 3/2 plus, minus 1 squared over 2 plus 2 times 1. And I'm thinking of this as 4 to the 3/2 is square root of 4 cubed. So that's 2 to the 3rd power, which is 8. So I'm getting 16/3 minus 16/2 plus 8. Minus, don't forget your parentheses. And don't we love ones and zeros? going to go ahead and distribute that. So I've got 16 thirds minus 16 halves plus 8 minus 2 thirds plus 1 half minus 2. And I'm hoping some stuff works out nicely here. 16 thirds minus 2 thirds gives me 14 thirds. Negative 16 halves plus 1 half is a minus 15 halves. Plus 8 minus 2 is plus 6. And I'm going to remind myself that I had this was my first part and this is my second part. And I'm adding the two of those together. So combining those, 14 thirds plus 4 thirds is 18 thirds. So altogether, 18 thirds, also known as 6, minus 15 halves plus another 6. Ending up with 12 minus 15 halves. And to get one answer, let's change this to 24 halves minus 15 halves is giving me 9 halves. Whoa, that was a lot of math. So, integrals. Good review of just kind of our general process of evaluating definite integrals. Obviously can be a bit of work. So I've got some kind of good news for you. Not that that wasn't doable. There's a second way to do this problem. And you might decide that the second way is a little bit nicer for us. So what if I told you only had to do one integral instead of two? Automatically, we're down to half the work, right? So how could I do this only one integral? Because clearly my top curve is changing. Well, the way that you could do this as a one integral problem is essentially... Whoa, that's not what I wanted to do. Yeah, I thought it would let me do it. I'm trying to spin my picture on its side. It's not going to let me do it. So you can do this. Take your paper and spin it 90 degrees counterclockwise. And what's going to happen is the yellow line that you see is going to change to your top curve. And then the parabola, the sideways parabola, is going to look like an actual parabola. And you're going to end up with something like this, a line and a parabola. And your top curve is now always the same. And your bottom curve is now always the same. So essentially, we can do right curve minus left curve. But what we need to picture is, if we're doing that, we're actually going to be taking rectangles this way. Instead of taking our rectangles sliced along our x-axis, we're taking rectangles sliced along our y-axis. So we're doing the equivalent of this, but obviously still facing the other direction. So we're going to be slicing and taking a small little bit. Our width of our rectangles is now a very, very small slice of our y-axis, and therefore we call it dy. And oh my goodness, we just changed it from dx to dy. We're going to be integrating with respect to y, not x, which you've seen before, just not in context of, you've seen it just in problems where I changed a variable. So what this is going to look like is integral. So I'm kind of giving you a new way to think about this. Area could be right curve minus left curve. And it's going to be with respect to y, so it's going to be dy. So that's what I want to set up. Now, if it's dy, we should know that everything now has to be in terms of y, not x. So remember this function y equals x minus 2, my yellow curve. I need to get that with a y instead of x. I can't put x minus 2 into an integral with a dy. So I'm actually going to take that and I'm going to solve for x. So if y equals x minus 2, add 2 to the other side, y plus 2 equals x. That's what I'm going to use as my y plus 2. So my right curve is y plus 2. Again, I'm saying curve, but that's my line. You should generally think of it as curve. Now I'm subtracting. My left curve is that radical x, positive and negative, which remember that was actually x equals y squared before I took the square root. So that's actually already set up for me, and I can just do minus y squared. That's the blue and the red, both of them. Okay, I would use parentheses, but I've just got one thing there at the end. And now I just need to set up my limits of integration. So be careful, we're not going to use 0 and 4. Those are my x values. I need y values. So I'm going from y equals, I didn't fill in this point down here, 1 comma, it's going to end up being negative 1. We can go back to our values that we found here, x equals 1 and x equals 4, and just plug those in. So if y equals x minus 2, then we've got 4 minus 2, which is 2, and y equals 1 minus 2, which is negative 1. So for the 1, we're getting negative 1, and for the 4, we're getting 2 for our y values. So I just hadn't found those y values earlier since we didn't need them. So we now know y values are 2 and negative 1. So I'm going to go from y equals negative 1 to y equals positive 2. So I drew a dotted green line before. I'm going to draw another dotted green line or solid green line. Think of it as we're going from there to there. That includes that entire region. If we did the integral without the negative y squared, we'd be doing all of this. And we don't want to do that, so that's why we're subtracting the y squared to get just that section. Cool. So we're ready to integrate, and here's the cool part. I got rid of the radical. This is going to be so sweet. I got rid of the radical. My integral is going to be 1,000 times easier to evaluate, and I only have one of them. So we'll compare how much work we did at the end. Actually, I'm ready to do the integral. I don't even need to do anything here. We could rewrite it if we want to and change the order. It doesn't really matter. So I'm going to go ahead, y squared over 2 minus 2y minus y cubed over 3, evaluated from negative 1 to 2. So, plugging in here. So I've got fundamental theorem of calculus. 2 squared over 2 minus 2 times 2 minus 2 cubed over 3. That's me plugging in the upper limit. Now plug in the lower limit. Negative 1 squared over 2 minus 2 times negative 1 minus a negative 1 cubed over 3. So we've got 4 over 2, which is 2, minus 4 minus 8/3 minus, don't forget your parentheses, 1/2 plus 2 minus a negative 1 cubed is a negative 1/3, so plus 1/3 since it's minus a negative. A lot of times my thirds will cancel out, so I'm just going to go ahead and distribute here and see what happens. Minus 2 and minus 1/3. So I've got negative 8/3 minus 1/3. That's going to give me a negative 9/3 or a negative 3 for those two. Negative 2 minus another 2 is negative 4, and then minus 1/2. So negative 7 minus 1/2. And I'm realizing I made a mistake here, so it should be a lot easier if we... Oh, there it is. I made a sign error, so maybe you caught that. I have no idea why this plus changed to a negative. That should be a positive. So I'm just fixing that real quick. Sorry about that. So that ends up being a negative. All those signs changed. So 2 plus 4. I should have gotten a 6 here, guys. Sorry about that. 1/2. This becomes a plus 2 because I distribute it. So I get 6 plus 2. Let's just redo this line. Okay, shouldn't have messed up my thirds because that sign was fine. So I've got 6 plus 2. So these two terms give me 8. The negative 8/3 and the minus 1/3 was my minus 3. And then I have a negative 1/2. So I end up with 5 minus 1/2, which is 4 and 1/2, also known as 9/2. That is looking familiar. So I'm going to shrink it all so you can see it. And what I'm doing is comparing what I did on the left of this line versus everything I did on the right. And this was a whole lot more work, plus uglier radicals with the radical x. So just another option. Both of them work, get us the same answer as long as we don't make a sign error. But gives us two options for how to solve this problem. I will say that sometimes integrating with respect to y becomes a necessity. This, I showed you one that we could do both ways, so you could see options and see that we get the same answer.